Today, we're diving into a massive environmental story that happens almost completely out of sight, deep inside the world's biggest ships. It's all about an invisible invasion that's been quietly reshaping our oceans for more than 100 years. And it all starts with a single, kind of weird question. I know, it sounds like the beginning of a really bad joke, right? On one hand, you have this microscopic bacterium that can cause absolutely devastating diseases. And on the other, you've got this little striped mollusk. So what on earth could possibly connect the two? And there it is. The answer is that they're both what we call invasive species. Basically, they're organisms that get a free ride to a new place, and when they get there, they don't just survive, they take over. And they can cause incredible damage to the local environment, the economy, and sometimes even our health. Their taxi of choice? The modern cargo ship. Okay, so let's get into it. The invisible invasion, how ships accidentally move ecosystems. To really get how this happens, we have to look at something that is absolutely fundamental to how modern ships work. It's a process that's crucial for safety, but it comes with this massive, hidden environmental price tag. That's a perfect analogy. Think about it. A ship drops off thousands of tons of cargo. All of a sudden, it's way lighter, and it's riding really high in the water. To keep it stable and to stop the hull from literally bending and breaking, it sucks in tons and tons of local seawater. That's ballast water. Then, when it gets to the next port to pick up new cargo, it just pumps all that water right back out, along with everything that was living in it. And this is the real kicker. When a ship takes on ballast water, it's not just taking on water. It's basically inhaling a giant sample of that port's entire marine ecosystem. Every little creature, every egg, every bit of bacteria, it's all coming along for a cross-ocean joyride into a brand new home where it might just become an invader. And here are some of the worst offenders. The International Maritime Organization calls them the 10 most unwanted. You've probably heard of zebra mussels. They've cost the Great Lakes region in North America billions, literally billions of dollars, because they clog up the water intake pipes for cities and power plants. And then there's the Cladoceran water flea. It hitched a ride from the Black Sea all the way to the Baltic, and now its populations are so huge they literally choke fishing nets. These things aren't just little pests. They are total ecosystem wreckers. So as global trade exploded, so did this problem. It was clear something had to be done. But getting pretty much every seafaring country in the world to agree on a single solution, well, that was a truly monumental task. And this timeline really shows you just how long and painful that process was. I mean, once the problem was officially on the radar, it still took 14 years, a decade and a half of tough negotiations, just to get the Ballast Water Management Convention adopted in 2004. And even then, it took another 13 years before enough countries signed on to actually make it official. The convention basically created a 1-2 punch. First, there was a temporary fix called ballast water exchange. The idea was simple. You dump your coastal water way out in the deep ocean and replace it with salty open ocean water. The hope was the salt would kill off the coastal creatures. But the real game changer, the permanent solution, is ballast water treatment. Now ships have to have technology on board to actively clean and sterilize the water before it goes back into the sea. And this is where things get really fascinating from an engineering standpoint. I mean, think about it. How in the world do you sterilize millions of gallons of water on a massive ship that's constantly moving? Well, it usually comes down to two main steps. First up is separation. You got to get the bigger stuff out. Most systems use incredibly fine mesh filters to catch things like tiny larvae and plankton. Step 2 is disinfection. This is where you go after the really small stuff, the bacteria and viruses that slipped right through the filter. And there are two main ways of doing that disinfection. The physical approach often uses powerful UV lamps. The UV light basically zaps the organism's DNA, just scrambling it so they can't reproduce. It's a clean method with no chemicals, but it can struggle a bit if the water is really murky. The other way is chemical, often using something called electrochlorination, which cleverly creates chlorine from the seawater itself. It works great, but you have to be super careful to neutralize any leftover chemicals before you discharge the water. And look, this isn't just a concept. It's a massive, real-world industry. This quote from Wärtsilä, one of the giants in marine tech, shows you just that. A huge business has sprung up to design, build, and install these multi-million-dollar systems on tens of thousands of ships. Following the rules has become big business. So, you've got the fancy new technology, but how clean does the water actually have to be? You can't just guess. And that's where the global standard comes in. And believe me, it gets very, very specific. This is the D2 standard. What it is a performance measure. It doesn't actually care how you clean the water, just that the end result meets these incredibly tough limits. For organisms 50 micrometers or bigger, that's about the width of one of your hairs, you're allowed less than 10 of them per cubic meter of water. To put that in perspective, that's like being asked to find 10 specific grains of sand inside a small room. It's an incredibly high bar. So why is this D2 standard such a massive leap forward? Well, you have to remember the old way, that ballast water exchange method. All it required was for ships to swap out 95% of their water. Not only was that hard to prove, it just wasn't very effective biologically. The new D2 standard is a game changer because it measures what actually matters: how many living things are left in the water at the end of the day. But of course, things can't be too simple. While most of the world follows that IMO standard, the US Coast Guard has its own rule, and it's even stricter. And the difference comes down to one tiny little word. The IMO measures viable organisms. That means, can they reproduce? The US Coast Guard, however, measures living organisms, period. So a creature that's been zapped by UV light and can't reproduce might still be technically living, and that means it would pass the IMO test but fail the US test. This single word difference is a huge headache for the global shipping industry. So, where does all this leave us? The rules are now in place, and the technology is being installed on ships around the globe. But you know what? The work is far from over. Staying compliant is a constant, ongoing process for every single ship on every single voyage. Yeah, it's not enough to just have the equipment. Every ship has to carry a specific management plan. They have to keep a detailed record book of every time they treat water. They need a valid international certificate. And they have to be ready for inspections at any time from port authorities who will come on board and make sure the systems are actually working and being used the way they're supposed to. So here's the final question. We've taken this massive, coordinated, global step to shut down one of the main highways for invasive species. But is it enough? This is a battle that's going to require constant vigilance, technology that keeps getting better, and really strict enforcement. The invisible invasion has definitely been slowed down, but the voyage to protect our planet's native ecosystems, well, that's a journey that never really ends.